Hey everyone. Okay, let's see. Just making sure the lighting's not too crazy today. Okay, so let's get started. We're going to talk about continuity, and then also at the end, we're going to go over a theorem called the Intermediate Value Theorem. As always, if you have any questions, put them in the chat. I'll see them as I'm talking and I can answer them. So continuity, real quick, just think about what you know about that word. The word continuous might come to mind. It's exactly what you think. If something's continuous, it doesn't break, it doesn't stop. That's what we're talking about, but specifically for functions. So we're going to use our limits and all those things we've been learning lately to be able to talk about this. So I'm going to start with continuity at a point. So at one specific point. So continuity, hopefully I spelled it right, at a point. And we're just going to generalize this and say point C. Okay, so our definition here is going to be to first let f be a function with a specific domain. So let me explain this real quick. So with domain, and it's going to be between two values. So you can have this be written two ways. It's going to be bracket a to b or parenthesis a to b. Okay? And so this just means, real quick, if you remember, if you have parentheses, you technically don't equal the endpoints. You don't actually plug in the end values. If you have brackets, you do. So brackets, you can plug in the a and the b into your function. So that's what that's saying. So your domain goes from A to B, such that some value that you are considering, some point, it's in between A and B. So such that A is less than or equal to C, which is less than or equal to B. So we are looking at this number here, C, inside our domain. Okay, this is sort of our background sentence. So with that in mind, let's talk about continuity. So I'm going to break this into three possibilities. So possibility one, your function f is continuous at C. So at that number in the middle here, somewhere in between, is continuous at C if the following limit is true. So if the limit as x approaches C of your function, f of x, equals f of c. All right, what does that mean? Think about it really quick, and then I'm going to give you two more versions. You're approaching this number c. We learned about one-sided limits recently. So this is saying that I'm approaching c from both the left and the right because you don't see the plus or minus here. So that means a two-sided limit. The limit of your function is, remember this notation, f of something? This means it equals whatever you get when you plug in that something, okay, that c value. That's what this is saying. So your limit, remember, in the past, we said a limit can exist even if your function has a hole at that point. This is saying for it to be called continuous, well, you basically have to fill in all the holes. Your limit has to be the same as if you were to plug in that number right into your function. Okay, I'll show you an example where you could fill in the hole that would have been part of the function. So two more versions of this. F is right continuous. Oops, that says right. It kind of crossed it out. Right continuous at C. And then I want to explain, when you read it like this, when it says right continuous at C, that actually means continuous, I'm going to abbreviate, from the right. From the right of C. And that's true if you take the limit of f of x as x approaches C with a little plus sign. Remember that? From the right. So from the right, and you get f of C. All right. Now, the third version of this is really, really similar to the second one. It's just from the left. So let me just describe that last one here. So f is left continuous, or that means continuous from the left. Okay, at C, so continuous from the left of C. And you can guess what I'm going to write. And that's true if the limit of f of x as x approaches C from the left is f of C. Okay. Now, I know it's a lot of definition here. I'll draw a picture and hopefully it makes more sense. But basically, if something's going to be considered continuous, either from the right, from the left, or two-sided, this one's two-sided, you have to plug in that value you're approaching, and you get the same thing that your limit approaches. Okay, so let me draw a picture. So something like this. Let's go ahead and draw it up here. I'll just get rid of this definition part, the first part, the let part. Okay, so let's say I have my x and y axis here. We just erased that the domain of your function went from A to B. So I'm just going to say A is here, B is here. This is my x-axis. Okay, so I'm plugging in x numbers from A to B. C is somewhere in between. Doesn't matter where, somewhere in between. I'm just going to place it like right here. Okay, it doesn't have to be in the middle, just somewhere in between. This is my y-axis, or f of x. And so my function can do anything, but I'm just going to draw it to do some kind of curve here. So I'm going to say that I have a point here, and it curves. There's a point at C, and it curves and does something else. Okay, this is a continuous function on this interval from A to B. And let's describe these other two parts, right and left continuous. So it's continuous at C, because look what happens. When I start to get close to C, here's C, there's x equals C. As I approach from the left, and when I approach from the right, I am coming right here to this point, which is actually f of C. This is the y value when I plug in C. So this has continuity on both sides, so this is continuous at C. I can approach from the left and the right, and I get the same number that I get if I were to just plug in C. Now, if I go toward an endpoint, let's go toward A. So if I'm approaching from the right, so I'm going to just say, so this is C. I'm sort of going to change this definition and just plug in the number A. So let's say I'm thinking about A. Well, A, if I come in from the right, it's only right continuous. And can you see why? I can't even approach from the left. So this function happens to be right continuous or continuous from the right at this number A. Okay, because I can't even come in from the left. And then very similar on the other end, if I approach B, I can only approach from the left, and it's continuous. There's no gaps, there's no jumps, there's no nothing crazy happening. So this function is left continuous at B. Okay, so just showing you the different continuities. The one that you're going to be using the most is the two-sided continuity, where I come in from the left and the right, and I approach the same number I would get if I just plug in that number. So let me show you some discontinuities, because there's not always continuity for a function, and then I'll show you an example of when you can remove one of them. I'll explain that. All right, how are we doing so far? Let me know if you have questions. Okay, so let's talk about the discontinuity. So this is like a note here. If f is not continuous at C, and I just want to specify in its domain. So So I'm only looking for numbers in the domain, numbers that are defined for this function, okay? Or this function is defined for those numbers. So if f is not continuous at c, then f is, and look at this technical term, discontinuous. Not very technical, it's pretty intuitive. If something's not continuous, it's discontinuous. Discontinuous at c, at that number. Okay? So if you find out something's not continuous, you just say it's discontinuous. So let me show you the types of discontinuity, because there's a few different ones. So types of discontinuity. And let's start with removable. So this is the one I've sort of mentioned briefly. So removable discontinuity. Removable. Let me show you a picture. I think it'll make the most sense. If I have a function, there's my xy axis, and my function does something like this. It's like a line, and then right here, for some reason, there's a hole in my graph, and then it keeps going. But my function is defined maybe right there. Okay, this is discontinuous. One easy way that I like to remember discontinuity or continuity at that in that regard is basically if you have to pick up your pen or pencil, it's discontinuous. The continuity is going to fail. And to draw this, I actually had to pick up my marker and draw that other point. Okay. But this is called removable discontinuity because you can actually make this continuous if you define your function a little different. So I will show you one example for this one, and then I'll show you the other types of discontinuity. Now I want to show you this example because we saw this in a previous section. So recall what happens when we consider the function sine of x over x. Okay, so let me remind you what you know about this. This was something we took a limit of recently, and when you take the limit as x approaches 0, it actually is the number 1. The limit is 1. But if you just look here, if I try to plug in 0, it's going to be undefined. So the limit is 1, but the function is undefined at 0. So what I can do in this situation is I can actually modify this function slightly by kind of making it a piecewise function and adding a piece to it. So I can say something like, well, I know that this is going to approach 1 when I get really close to 0. So if I actually want to plug in 0, so let's say x is 0, I can just go ahead and define that my function is 1 right there. And then over here I'll say something, this is for all the numbers other than x is 0. Okay. So what that would look like if I draw that, let me just kind of squeeze it in down here. Sorry, just really quick graph of this one. It looks like this, like the graph does something like this, but there's actually a hole right here when you try to plug in 0. So basically what this removable discontinuity is doing is you're just like redefining your function to fill in this hole. When x is 0, y is 1. And then I wouldn't have to pick up my pen to draw that graph. So that's removable discontinuity. So let me give you the other types. So let's get rid of this picture. All right, the next one is jump discontinuity. So you might be able to guess what that's going to look like before I even draw it, just based on the name. So here's a picture of a graph that has this type of discontinuity. So let's say my function is doing something like this, and then right here, it jumps to down here. Okay, so at that number, there would be discontinuity. This function would then be considered discontinuous. And it's, again, if you have to pick up your pen or pencil to draw it, it's discontinuous. And it's jump because I jump from here to here. Okay? The next type is infinity, or infinite, if you want to think of it like that. So infinity. So let's draw that one. And we'll talk about this soon, actually, in the next section. We're actually going to go over limits that do something with infinity. So this one, the graph does something like this. Let's say I'm thinking about right here. on the y-axis when x is 0. Maybe the graph does something where it's continuous all over here, but then when I get real close to 0, it just kind of shoots up to infinity. And then again, I'm trying to get close to 0, but my graph does something like that over here. So this would be another discontinuity, because again, I had to pick up my pen to draw both parts of this graph, but this time it shoots up to infinity. It could also shoot down to negative infinity, and it's still considered the same type of discontinuity involving infinity. And then the last one to show you is oscillating. So, I always spell this wrong. Oscillating, I think that's right. And this one I'm just going to kind of scribble. Let's say I'm approaching 0. My graph is doing something, and then when I get close to 0, it's oscillating like that, and then maybe it slows back down after. So too much is going on for me to figure out and say that it's exactly one value right in there. So those are different types of discontinuity that might come up, but a lot of times we will be working with continuous functions. Okay, so what I'm going to give you now is a test to figure out if the function is it continuous, and it's really an intuitive idea. I'll explain it, but it's like a 3-part test. Okay, so that's going to be our continuity test. So if we have these 3 things true, our function is continuous. So I'll say if all 3 are true. Number 1, f of c exists. Okay? If I plug in this number I'm trying to approach, I'm going to get an answer. That's sine of x over x example. That was not true because when I plugged in 0, it was undefined. This is saying when I plug in some number I'm approaching, I'm going to get an answer. That's number 1. Number 2, the limit as x approaches c of f of x exists. Okay? So this just means that when I'm approaching this number c, I'm going to get a limit value. In the past, when we first learned about limits, we learned that these two do not have to match for the limit to exist. Like I just showed you, when I plugged in 0 into that function for sine, the limit still existed. It was still 1. So that's what number 2 is saying. The limit happens to exist. Now here's the main one here. Number 3, put these together. And that implies continuity. So the limit as x approaches c of f of x is f of c. Okay, so it's actually pretty much our definition that we wrote down already, just sort of broken into steps, and we call that the continuity test. If you can plug in c and you get an answer, if you can find the limit as x approaches c and you get an answer, and then those 2 answers match, that's when you get continuity. Okay, so again with that, let me show you really quick. You don't even have to draw this, but if I had something like this, that first graph I drew, this would fail the test because this f of c would exist, this limit would exist, but they would not be the same number. This one's like up here. I don't know what that number is. I'll just make it up. I'll say it's 4, and this is 3. So they're not the same number. So it would fail part 3. Okay. So for it to be continuous, this has to exist, the limit has to exist, and they have to be at the same y value. And again, the easiest way, just think of not having to pick up your pencil, and that would be continuous. Okay. So all 3 of those are true. Your function is therefore then continuous at c. So let me add that in here because I'll just say implies that your function f of x is continuous at x equals c. Let's just get that into this definition here. All right. So let me show you an example of a really interesting function. It's called the greatest integer function. It comes up when you're working with, I think, electronics, because it does like this jump, and it's this idea of like switching from zeros and ones with electronics and circuits. So it's a pretty interesting function. It's called the greatest integer function. And I want to show you this one to kind of talk about the continuity even more. So for example, let's consider f of x equal to, and if you've never seen these symbols before, it kind of looks like an L and then a backwards L. And then remember, math is actually a language with symbols. So when you see symbols, you kind of have to take a moment in your head and translate them into what they're really asking you. So when you see these symbols, this is how you can translate it in your head. Greatest integer function. And I'll explain it even more. So greatest integer function. And so that might still not mean anything to you. So what you can say here is that this equals the greatest integer. And real quick, integers are just our whole numbers, but to include the negatives. So 1, 2, 3, -1, -2, -3, zeros included. So this equals the greatest integer less than or equal to x. All right, so one more time. When you see these symbols, you actually have to take that moment and realize that it's asking you to think about this. So this is how you translate these symbols. I'm going to plug in x numbers, and my output, my f of x, is the greatest integer that's less than or equal to this number. So let me give you a few values, and then we'll actually graph this function. So let's go over here with the values. So let's see, I'm going to plug in 0. So I'm going to say f of 0 into our greatest integer function. We're going to go ahead and say f of 0.5, plug it into our function. I'm just picking a few. Next, I'm going to pick f of 0.99 into our function. And then my last one I'm going to plug in is 1. So f of 1 into our function. Okay, so I didn't find any of my y values yet, but I plugged them into my function and I have to determine the y value. So do it with me. I plug this number into this greatest integer function, and then the output is this, the greatest integer less than or equal to that number. And remember what I said for integers, the negatives and positives, but whole numbers, to include 0. So the greatest integer less than or equal to 0 is 0. The greatest integer less than or equal to 0.5, 0.5 is not an integer. So it's saying what's the biggest number that's still smaller than or equal to 0.5? Well, it's 0. The first integer closest to this number, but less than or equal to it. How about 0.99? The biggest number that's still less than or equal to this number, that's an integer. 0.99 is not an integer. It's 0. All right, here's where it jumps. How about the greatest integer less than or equal to 1? Well, that's 1. So the idea here with this one is you can plug in anything between 0 and 1, and you're going to get out 0. The moment you plug in 1, you're going to get out 1. And the same thing's going to happen, 1.2, 1.3, 1.4. You're going to get out 1, and then it's going to jump when you plug in 2 and 3 and so on. So here's what the graph looks like. Another name for this function is called the step function, and you'll see when I start graphing it. So I'm going to plot just a few parts of this graph. Let's just put some tick marks here. Okay. So my x and y axis, let's change colors. So I'm just going to start with the values we found and then plot a little more for you. I plugged in 0, I got out 0. I plugged in 0.5, I got out 0. I plugged in 0.99, I got out 0. But the moment I plugged in 1, I actually had to jump up here to 1. So think about it. If I had plugged in 0.999999999, got so close, the output is still 0. So the way we show that is we actually put an open circle right here, just to show whoever's looking that I got so close to plugging in 1, but I never actually plugged in 1. And when I did plug in 1, I got up here. Okay? And so everything in between here would be part of your graph. So I'm going to connect these because I only found a few points, but there's infinitely many right there. And so the idea is the same thing would happen if I plug in 1.2, 1.3, 1.99. And so this starts to look like steps that have a left endpoint that's closed and a right endpoint that's open. So same thing down here. So that's why I was saying the other name for this is called the step function, because it kind of looks like steps. All right, now let's talk just for a moment about the continuity of this function. If there's any continuity, there's a little bit. Okay. All right, so is it continuous everywhere? Definitely not. And it's because you do a whole bunch of jumping. So it has a bunch of discontinuity from jumps. But there is a little bit of continuity, and I'll explain. So f of x is discontinuous at x equals an integer. Every time we're looking at an integer, that's when we do a jump. Here's 0, okay? I jumped down here at 0, from -1 to 0. I jumped from 0 to 1 here, that was at 1. I jumped at 2, I jumped over here at -1, I jumped at -2. So all of the jumps happened at integers. So this function happens to be discontinuous every time I try to plug in an integer. Okay. All right, so how about any continuity? So f is, I'm going to say blank continuous. I want you to think about it. Blank continuous at x equals integers. Any integer. All right, you only have two choices here, either left or right. At all the integer numbers, is our function continuous from the left or from the right? So let's go over here. You maybe already see it. I'm going to pick 1 for my integer. When I'm at 1, this point, if I come in from which way, is it continuous? From the right, okay? So right here, if I come in from the left, I'm actually down at this next piece. So if I come in from the right of 1, I'm approaching 1. Same thing at 2. When I come in from the right of 2, I'm approaching 2. If I come in from the left, I'd have to jump up to get there. So it's actually continuous from the right. So it's a right continuous function at all the integers. So even though there wasn't full continuity, I had to pick up my pen a lot to draw it. There was some continuity every time if I come in from the right of all these integer numbers. All right. And then there's no left continuity on this one. Okay, so that's sort of the intro to the continuity. What I'm actually going to give you next is some properties and talk about continuous functions. And we'll get into slightly more complicated limits. And then we're going to end with what's called the Intermediate Value Theorem. So let me just mention a very, very intuitive sentence really quick, and then I'll give you the properties. So by definition, when you're talking about continuous functions, okay, which we're going to talk, usually we're dealing with continuous functions, it's basically just this, a function that is continuous at every point in its domain. Okay. So this one here, like I just said, it's a pretty intuitive sentence, but it's actually the expansion of what we've been talking about so far today. I've sort of been only telling you about continuity at points, at this point, at this point, at this point, at C, at integers. Now I'm saying if you generalize that, if you figure out your function is continuous everywhere, at every single point in your domain, you never have to pick up your pen the whole time you're drawing from A to B, then you call that a continuous function. Before this moment, I was actually saying continuous at a point. Now I'm saying continuous functions in general. So just sort of broadening this idea here for you. Okay, so let me give you the properties. And these are going to be pretty straightforward, you'll find. A lot of times when we deal with properties, they are things that you kind of would guess would be true. So properties of continuous functions. And I have 7 of them for you. We'll just go through them kind of quickly. Let me give you a background sentence. It's sort of like a fine print that has to be true to make these properties true. So we'll say if F and G are continuous at x equals c, and then we'll say then the following are continuous. I'm going to abbreviate continuous at x equals c. So just my background sentence, and then here's our 7 properties. Number 1, if you add f and g, you're going to get a continuous function. So if I have 2 functions, I already know they're continuous. If I decide to add them together, the result is continuous. Number 2, same thing with subtraction. If I subtract 2 continuous functions, the result is continuous. Number 3, if I multiply my function times some scalar, I'm going to just say k for some number. So k times f is continuous. And this is for any number k. Right? So if you know you're working with a continuous function and you just times it by some number, all your outputs, that answer is still a continuous function. Number 4, if you multiply 2 continuous functions, then the result is continuous. Number 5, if you divide 2 continuous functions, but this one has like a little extra piece, and think about why. Anytime you divide, you always got to be on the lookout for one thing, right? You cannot divide by 0. So I just have to say that when you plug in this number c, this cannot be 0. So you just got to add that because we're dividing by g. So this says g of c. Can't be 0. Just to kind of make sure I don't do that. Then number 6, your function raised to an exponent would also be continuous if you're starting with a continuous function. Now this one, you just have to say that n is a positive integer. Now I'm kind of squeezing this into the side. Hopefully you can see it. This says n is a positive integer. So we're not talking about like fraction exponents. We're not talking about negative exponents. We're just saying like f to the first power, f to the second power, f to the third power, things like that. And then number 7 here, if you take a root, so you say like the nth root of my function, square root, cube root, fourth root, so on, that's going to be continuous as well. And same thing holds true over here. This has to be, for n, a positive integer. So n is a positive integer. Okay. So I'm going to give you a couple more facts. So these were the properties. You don't really have to like memorize them. As long as you know that you're working with continuous functions, you basically can kind of just take this stuff for granted that it's true for now. So you don't have to prove it. You just can say, okay, I'm working with continuous functions. I'm going to be allowed to multiply. I'm going to be allowed to raise it to a power and so on because the result will stay continuous. So let me talk about composition of functions and then I'll show you an example. So let's see what you remember really quick. Composition of functions, maybe that sounds familiar. That's when you create a new function by actually putting one function into another one. So think of composing. When you compose something like a song, you're placing notes together, musical notes, to create something. So a composition function, you're just using functions to compose a new function. And so we have a fact that has to do with continuous functions when we compose new ones. So composition of continuous functions. I'm going to abbreviate continuous. So composition of continuous functions. When I'm composing a new function from two continuous functions. If f is continuous, I'm going to abbreviate again, continuous at C, and G is continuous at f of C. Let's move this. Okay. There's a reason why I put f of C. It has to do with the composition I'm about to do. So f is continuous at C, G is continuous at f of C, then G composed of f is continuous at C. All right, so if you've learned about composition in the past, you kind of remember that's not a O, it's not a the letter O, it's actually a symbol, it's a math symbol, kind of like plus minus, it's an operation. So when I read it right now out loud to you, I said G composed of F. So if you need to, write a note for that. G composed of F. It means I'm actually putting F inside of G. So if you want to rewrite this with symbols, it looks like G on the outside and then F of C on the inside. And I'll say is continuous. So basically, if I know that I have two functions, one of them is continuous when I plug in this number C, then the other one is continuous when I plug in both of those at the same time, f of C. Okay? Then I can put them together and do this composition, and the result is continuous. All right, it's going to mean a little bit more to you after I show you this example. Let me give you something about limits, and then I'll do an example that involves this idea of continuous composition of functions. Okay, so let's mention something about the limit of continuous functions real quick. So limits of continuous, abbreviated again, functions. And here's my background sentence really quick, my if part. If the limit of f of x as x approaches c is equal to some number, I'm going to go ahead and call that number b. Okay, so it's equal to b. And if g is continuous at the point b, So far that's like my background, then it's going to be then this happens. So this has to do with this composition idea already. I have the limit equals some number, and then I'm saying that this other function happens to be continuous at that number. Okay, then the following is true. So then the limit as x approaches c of this composition, g composed of f of x actually just equals g of b. Okay. So this will make sense, I think, a little more with this example I'm going to show you next. But basically, it's just saying, if you're going to compose functions, as long as everything was kind of continuous to start with, then the limit is going to be continuous, and it's actually just going to be you plugging in this original output for the limit into this outside function. All right, so here's this example. Let's find, if possible, the limit. So we're going to say the limit as x approaches pi over 2 of cosine of 2x plus sine of 3 pi over 2 plus x. All right, I kind of ran out of room there. Let's see. I don't think you can see that. Let me rewrite it down here. So limit x approaches pi over 2 cosine 2x plus sine of 3 pi over 2 plus x. All right, hopefully that's better. Okay. This looks complicated, right? Find this limit of cosine of something. Okay. Well, what we can do now is actually just use this idea, because this is composition, this idea we just talked about. So officially, I'm going to go ahead and say that this cosine of something is the outside part. It's g. Cosine of x, if you want to say it like that. So this is my outside function. My inside function, f, is all this other stuff. Okay? So what we can do, based on the things we've talked about here, is we can actually address this limit by separating it. Let me move this. And taking maybe the more complicated part or the outside function just out of the way for a while. And so I'm going to go ahead and say that this is equal to cosine of the limit. So you can almost think of it like switching, but you're basically undoing the composition and bringing the limit inside here first because of this statement we just talked about. Okay, so this is just going to be the limit of the inside part can get plugged in to our outside function. So we're going to take the limit as x approaches pi over 2 of all that inside stuff. 2x plus sine 3 pi over 2 plus x. Okay. And now we just try what we can. Remember, always try direct substitution. And if that doesn't work, then try something else. It's going to work on this one. So if it doesn't, then you try one of your math techniques or math tools like multiplying by 1 or multiplying by the conjugate or things like that. But direct substitution will work here. So cosine of, and the moment I'm direct substituting, I'm taking off the limit notation because I'm plugging in. So I don't need the LIM anymore. So this is 2 times pi over 2 plus sine of 3 pi over 2 plus pi over 2. And we just start simplifying, okay? So right here, this is going to just be pi. This is going to be sine over here of 4 pi over 2, which is 2 pi. And all of this, we are taking cosine of this. All right, I'm bringing you back to your trig for a minute. Sine of 2 pi, think of your unit circle. You're back here at the x-axis. This is 0. All right, so this is cosine of pi. Again, unit circle, cosine of pi. You're circling around to negative 180 or to 180. The answer is negative 1. All right, so this limit, all of that, gave us negative 1. Okay, so the idea is you can actually, when you have composition of functions like this, everything was continuous here, so you can kind of undo it and do the limit of the inside part first, and then bring in that cosine or that outside part later. All right, I think we're, let me give you 2 more facts, and then we're ready for the intermediate value theorem. Okay. So these facts are really, really intuitive or straightforward, but I do want to mention them to you really quick. So we have just a couple of theorems. So the theorem is like a statement that's been proven mathematically. And so the first one is if we're going to talk about a polynomial, so I'm going to call it P. P of x is a sub n times x to the n power plus a sub 1 times x plus a sub 0, then, and I'll explain that notation really quick, then the limit as x approaches c of p of x is p of c. Okay, that's our first of two statements I'm going to give you here. This is just saying if you have a polynomial, so this is a general way to write a polynomial if you've never seen it before, but the things you've seen are things like x squared plus x plus 1 with numbers, okay? So this is just saying in general. So you don't even have to write this. Just this means the same thing like 3x squared plus 2x plus 1. That's the same as this, okay? So if this says if you have a polynomial and you're taking the limit, then it's the same exact thing as if you just plug in this number here. So with polynomials, direct substitution will work. Basically is what we're getting at there. And so then what that has to do with what we're talking about in this section is that every polynomial is continuous. So every polynomial, if you graph them, you can try it. Like use a graphing website or utility and just plug in random polynomials, and they're never going to have a jump or a hole in them. So every polynomial is continuous, and that's because, let me get rid of this real quick, because the limit as x approaches c of p of x equals p of c. All right, so we have a theorem that said this, but we had a continuity test, that 3-part test, that said if this is true, then it's continuous. So we're kind of just putting together what we talked about earlier, and with the fact that polynomials are continuous. These can kind of be thought of in both directions. That if you know this is true, this is continuous. If this is continuous, this is true. Don't have to do a whole lot with that, but I just want you to be aware that that's true for polynomials. So now the last thing is what's called the Intermediate Value Theorem. So in math, in your time in math classes, what you find is there's always like a handful of theorems that end up like seeming pretty important, or they come up over and over again maybe. There's something called the fundamental theorem of calculus we'll learn eventually. So there's some fairly important theorems. This is one that's amongst like ones you see more often. So let's talk about it. So Intermediate Value Theorem. And before I even tell you anything about it, you can kind of sort of get an idea for it just based on the title, Intermediate Value. Some number in the middle. That's how you can translate it. There's a value in the middle somewhere. Intermediate is like in between, in the middle. Okay, so that's what this theorem is going to be about. So any theorem has like a kind of like a fine print statement, an if statement. So let me give you that part first. So if f is a continuous function, let me abbreviate function, on a closed interval. So if my interval is closed, you're going to use brackets. So I'm going to say brackets from a to b. Okay. And if y sub 0, we call this y naught usually. So y naught is any value between, so before I'm going to keep writing, I'm saying this y value is between two other y values, intermediate value. So it's between two other y values. How do I write y values? Well, I use f of that x value. So between f of a and f of b, and that's the if part, then y naught is equal to f of c, and this is for some c in the interval from A to B. I will draw a picture to make this make sense, but it's really straightforward once you see it. Okay, so you're starting with a continuous function, and basically that word continuous there is kind of a big deal, and it's why we're able to conclude what we conclude with this theorem. So let me draw the picture, and I think once you see it, it might make more sense. So here's my picture for you. I'm going to have my y-axis here, my x-axis here. My domain of my function goes from A to B, so I'm going to just kind of make some marks where I'm going to place A and B. And now I don't know anything other than what's given in this statement, so I'm going to kind of go along in this statement and place things. So I know I have a continuous function from A to B. I do know that y naught is somewhere between f of A and f of B. So let me start with f of A and f of B. And you can kind of just make this up, and anything you make up will work here, and it's because this is a continuous function. So I'm going to say that f of A is right here. So that's my f of A. That's my y value when I plug in A. And I'm going to say f of B is maybe up here. And just so you know, they don't have to be one high and one low. They can actually be on the same line or switched. Doesn't matter. You're going to get the right idea here. So this says that y naught is between those, somewhere between. So I don't know where, but let's say here. Okay, so that's my first part of my sentence so far. All right, now, then the claim is, if that's true, okay, if y naught is between f of A and f of B, then y equals f of C. Y equals the output for some number in here. Okay, why can I say that that's true? So this is claiming, this theorem, that this y value came from some x value. Why am I allowed to say that's true? Why is this theorem going to work? Right here. This one word right there. Continuous. If a function is continuous, you don't pick up your pen to draw it. And so it doesn't matter how squiggly I draw this function, as long as I draw a function that's continuous, I have to pass through this point. And it has to meet some c value on the x-axis. So I'm just going to draw a nice one. I'm not going to do something too crazy. But let's say my function does something like that. I kind of missed. All right, right there. That's all it says. Okay. So you might be thinking, oh, I can probably come up with a drawing that will make this false. Remember, it still has to be a function, and functions have to pass the vertical line test. So you can't draw a vertical line. That wouldn't work. But anything else you can possibly draw. And also you can't, so vertical line test, you can't draw something squiggly like this either. That's not a function. Any drawing you can come up with here, though, that is a function, you're going to end up saying that this y value comes from some x value down here. I'll do it in another color just so you can see. I'll just sort of make a new drawing really quick just to show you. You don't have to draw this version. But even if I didn't say it was this point, it could be anywhere. So I'm going to pretend, you don't have to draw this. Just kind of pretend this is a new function. So maybe I drew my function like this. It did something else. Well, if I kind of line this up right here, right there, that would be my c value. Okay? Right there. There's actually more than one in this case. So let's get rid of some of that though. All right, the idea is you can kind of just scribble whatever you want here. So vertical line test to draw a function. That's what this theorem is saying. There's some point in between because you didn't pick up your pencil that corresponds from this y value to this x value. And that's what it is. So let me just show you real quickly an example where you might have to use this. We'll just stick with blue marker for this last one. Let's say someone asks you something like this. Show, or you're asked to prove this. There exists a root between let's go with 1 and 2 for the function f of x equals, let me just write that down here, f of x equals x cubed minus x minus 1. Okay, so I want to show you this one because this is the type of thing you tend to come across when you're doing more technical math stuff. So the idea is super simple. If you don't pick up your pen and you have a y value, it must have came from some x value in that domain. This is more of the complicated side of it where you have to actually say, well, how do I use this theorem I just learned? So let me explain. This exactly right here just uses this theorem we talked about, even though it seems more complicated. Show there exists a root. First of all, you have to know what a root is. A root is just when your function equals 0. So this part here, even though it uses the word root, this just means f of x equals 0. Y is 0 is what that means. Show there's a 0 for y, somewhere between 1 and 2 for this function. Okay. If you graph this, if you use a graphing utility, you will see that you're going to hit the x-axis, which is when y is 0. But the way we show it is we basically use this theorem and just say, by this theorem, it's true. And I'll show you really quick. We are told where to look. We're told to look between 1 and 2. So I don't have the drawing of the graph. It's got to do some kind of river shape because it's a cubic function. But basically, if I kind of just zoom in on the part of the graph I'm interested in, I'm really just interested in what happens between 1 and 2. Okay, so let me just start there. Here's my x-axis, here's my y-axis. You don't really have to draw this. I'm just trying to make you understand it visually. What happens when x is 1? Well, let's plug that in. So when I plug in 1 into this function, I'm going to get 1 cubed minus 1 minus 1. So that's going to be negative 1. Okay, let me plot that. So 1, negative 1 is a point on my graph. Okay, how about when I plug in 2? So when I plug in f of 2, I'm going to get 2 cubed minus 2 minus 1. So that's going to be 8 minus 2 minus 1. So that's going to be 5. Okay, so I plugged in 2 and I got out 5. I'm just going to mark it up here. Now, we just wrote down this theorem and a fact. First of all, this is a polynomial. And we said polynomials are continuous. So if this is a continuous function, and I have to connect this point to this point when I draw my graph, look what has to happen. I have to, at some point when I'm drawing my graph, whatever it looks like, I have to somehow connect them and pass through the x-axis when y is 0. I don't know where exactly. I mean, I can do more work to find it, but this is the proof. I could say by the intermediate value theorem, because on the left, so on my interval, the left side of my interval, I'm below the x-axis. The right side of my interval, I'm above the x-axis. So because I can't pick up my pen to draw my function, somewhere in between, I passed y equals 0. That's it. That's it for the proof. To show it in this case. So we can show it and you can say it in words like what I just said by the intermediate value theorem because f of 1 was negative and f of 2 was positive. Somewhere between 1 and 2, some x number here, y is 0 exactly because 0 is between negative and positive numbers. So that's the intermediate value theorem. Don't overthink it, hopefully. It is just this idea of not picking up your pen, so you have to cross through some points along your path. I think we did it. So that is it for this section on continuity and the intermediate value theorem. I'll stick around for a minute, type in any questions you might have in the chat. And hopefully this was good for you guys. Just so you know, the next video when we meet, it's going to be about limits involving infinity, which I kind of mentioned just a little bit today with that discontinuity. All right. if that's it, then I'll see you guys around. And if you have questions and you didn't type them, go ahead and put them in the comments after it posts. And you can always email me as well. Okay, everybody. Have a good day.